Uh, Dear students, can you hear me? Dear students, can you hear me?
Yes,
Yes,
sir.
sir.
So after revision, let's start studying about the enthalpy of atomization. Atomization of hydrogen. What is the meaning of atomization? Let us try to understand. That atomization of hydrogen, that is what something we want to understand first. You can see that we have the molecule of hydrogen. This molecule of hydrogen is converted into two atoms of hydrogen. So one molecule turns into atoms. This is the energy change during this reaction is known as the enthalpy of atomization. So H atoms are formed by breaking H bonds in the hydrogen, and the enthalpy change in this process is known as the enthalpy of atomization. Enthalpy change on breaking one mole of bond completely to obtain atoms in the gas phase is called enthalpy of atomization. Once again, enthalpy change on breaking one mole of bonds completely to obtain atoms in the gas phase. Please remember that the atom should be obtained in the gas phase. This is what it is the important condition. So after the atomizations, the atom must be obtained in the gas phase, and if the atoms are obtained in the gas phase, then such energy is known as the enthalpy of atomization. In case of diatomic molecules like dihydrogen, the enthalpy of atomization is also bond dissociation enthalpy. So here, my dear students, as the bond or there is only one bond present, so during you can see that there is only one bond present. So during this atomization process, actually the energy which is exchanged is also known as the bond dissociation enthalpy, because when there is only one bond present, the enthalpy of atomization and enthalpy of bond dissociations are same. The other examples of bond dissociation enthalpy is this, that you can see that methane, when it is bonded, uh, when it is released to give us the 1 carbon and 4 hydrogen, and here we can understand the enthalpy of atomization is 1665 kilojoule per mole. Here products are only atoms of carbon and hydrogen in a gaseous phase. Remember that the carbon and hydrogen, or the element that we form after atomization, they should be in the gaseous phase. Same way, my dear students, when sodium in solid phase is converted into sodium in gaseous phase, the enthalpy change for this reaction is 108.4 kilojoule per mole, and this, in the above case, enthalpy of atomization is equal to the enthalpy of sublimation, because this solid is directly converted into gaseous, and that is why this enthalpy of atomization can be considered as an enthalpy of sublimation. So my dear students, in various cases, we have seen that the enthalpy of atomization can be considered as either the enthalpy of bond dissociation or enthalpy of sublimation in some cases. Now, my dear students, we want to understand the bond enthalpy, which is known as the delta bond H bar. So let us understand what is bond enthalpy. Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond, and energy is released when the bond is formed. Please remember that energy is required to break a bond, and energy is released when a bond is formed. So when a bond forms, energy is released. When we want to break bond, energy is required. It is possible to relate heat of reaction to the changes in the energy associated with the breaking and making of bond. Please remember, or please understand it well. If you don't understand, please ask me. It is possible to relate heat of reaction. We can relate heat of reaction, my dear students. The heat of reaction, we can relate it to the change in the energy associated with breaking and making of bonds. So heat of reaction can be related to the energy changes during the breaking and making of bonds. With reference to the enthalpy change associated with the chemical bonds, two different terms are used. So now we want to understand those two terms which are used when we want to study about the bond dissociation or bond enthalpy. These two terms which are used in the thermodynamics are bond dissociation enthalpy and mean bond enthalpy. So please understand here that for same bond enthalpy we can use two type of bond enthalpy, or there are two terms used for bond enthalpy. One is bond dissociation enthalpy, another one is bond mean enthalpy. Let us see what is this. Let us discuss these terms with reference to the diatomic and polyatomic molecules. So first we want to study about the diatomic molecules. We have seen that in diatomic molecules there is only one bond present, and that is why their bond enthalpy or bond dissociation enthalpy is equal to their enthalpy of atomization. Bond dissociation enthalpy on hydrogen is 435.0 kilojoule per mole. The enthalpy change involved in this process is called bond dissociation enthalpy of HH bond. The bond dissociation enthalpy is the change in the enthalpy when one mole of covalent bonds of of a gaseous covalent compound is broken to form products in the gas phase. Once again, let us read or let us understand the definition. The bond dissociation enthalpy is the change in enthalpy when one mole of covalent bonds of a gaseous covalent compound is broken to form the uh, products in the gas phase. So, my dear students, for diatomic molecules, we can write enthalpy of atomization is equal to bond dissociation enthalpy. You can see that even for Cl2 gas that gives 2Cl gas, or O2 gas that gives 2O gas, here the bond dissociation enthalpy for chlorine is 242 kilojoule per mole and for oxygen is 428 kilojoule per mole. And you can easily understand that this bond dissociation enthalpy is actually the enthalpy of atomization too. Remember that in oxygen we have double bond, and that is why the enthalpy of atomization is little higher than the chlorine. So this is how we can even understand that double bonds are more stable or more stronger than the single bonds. Now we want to study about the polyatomic molecules, where the number of atoms present in a molecule is more than 2. So in case of the polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. So my dear students, if we have a single molecule, in that particular single molecule, we have the various numbers of bonds present with it, and these bonds which are present there, they are not similar. When we break them, we require different amount of energy needed for each bond to be broken. A polyatomic molecule like methane, the overall thermochemical equation for the enthalpy of atomization, we can see here, my dear students, that CH4 gas that gives C gas plus 4 hydrogen, enthalpy of atomization is 1665 kilojoule per mole. In methane, all the four CH bonds are identical in both length and energy. So, in methane, if we study, then all the bonds which are formed between the carbon and hydrogen, they are equally long and they are found to have equal energy. Oh, sorry. However, the energies required to break the individual CH bond in each successive step differs. So during each successive step, sorry, the amount of energy which is required, it actually differs. So if you have methane, then you first break the hydrogen bond and the energy sorry, required is 427 kilojoule per mole. Now we have CH3. From CH3, if we remove one hydrogen, then the energy required is more than the previous one. Then when it comes to CH2, when one hydrogen is removed, even the energy required is more than the second step. When we have CH and we remove one hydrogen, then the energy required is little lesser. So here you can see that for all these four steps, the amount of energy which is required is different. And we take the sum of all this energy, like delta H is equal to H1 plus H2 plus H3 plus H4. This is your H4, this is your H3, this is your H2, and this is your H1. And by doing the sum of all this energy, we find that when we break all the bonds of CH4 and take the atoms of carbon and hydrogen, we get this amount of energy with us. That is 1665 kilojoule per mole. Now, for all the four bonds, instead of, so here I have done it that the bond dissociation enthalpy of or the enthalpy of atomization would be the for H1, H2, H3 and H4, and by doing this now for any CH bond in CH4 we determine mean bond enthalpy. So here you can see that while breaking the bonds, the various amount of energy are being needed. So for single bond, we have to, for single bond that is present into methane, that is CH bond. For each bond, if we want to uh, understand the bond dissociation enthalpy, then here we will have to take the mean bond enthalpy for CH bond, and that is why the bond dissociation enthalpy for CH4 or bond enthalpy for CH4 is taken as the average of it, and that is why the enthalpy of atomization is divided by 4 because 4 bonds are present, and thus the bond enthalpy for CH bond in methane is 416 kilojoule per mole. This is how, my dear students, we understand about the various enthalpies. We find mean CH bond enthalpy in methane is 416 kilojoule per mole. It is found that the mean bond enthalpy, that is CH, differs slightly from the compound to compound but does not differ in a great deal. So if we check out in the different compounds, this CH bond enthalpy differs, and it differs not in a great amount, but still it differs in various compounds. For example, CH bond enthalpy is different in CH4, CH3NH2 and CH2Cl. If you look into the data, we can come to know that the carbon hydrogen bond that is present in the various compounds like methane, nitromethane and chloroethane, this bond enthalpy differs with each other as far as the amount of energy or bond dissociation enthalpy is concerned. Now, using the hash law, bond dissociation enthalpy can be calculated. So, this is again one of the very good application of the hash law, that using the hash law we can calculate the bond dissociation enthalpy. The symbol used for bond dissociation enthalpy and mean bond enthalpy is same. So whatever the symbol that we use, either we use it for bond dissociation enthalpy or bond mean enthalpy, we use the same kind of symbol. The reaction enthalpies are very important quantities as these arises from the changes that accompany breaking of old bonds and formation of new bonds. So reaction enthalpies are very important, and why they are important? Because they arises from the changes that accompany the breaking of bonds and formation of new bonds. So both the way, the breaking and forming of new bonds are included into the enthalpy of reactions. We can predict the enthalpy of reaction in a gas phase if we know different bond enthalpies. So if we are aware of the different bond enthalpies of reactants and different bond enthalpies of products, we can come to know about the bond enthalpies. We can come to know about the bond dissociation enthalpy, or we can calculate the bond dissociation enthalpy using the data given. The standard enthalpy of reaction is related to bond enthalpies of reactants and products in the gas phase. So we can find out, to calculate the bond enthalpy, we can find out the formula that enthalpy of reaction is equal to bond enthalpy of reactants minus bond enthalpy of products. Please remember, my dear students, that here we have taken the bond enthalpy of reactants first, and from that we have reduced, or we have deducted the bond enthalpy of products. Generally, when we find out the enthalpy of reaction, we write enthalpy of products minus enthalpy of reactants. But here, in case of the bond enthalpies, we use this formula, that summation of the bond enthalpies of reactants minus summation of the bond enthalpies of products. This is a unique formula, or this is something different from the other formulas, so better you remember this. But remember that the value should be given into the bond enthalpies. This relationship is uh, particularly more useful when the required value of enthalpies of formations are not available. So when the enthalpies of formations are not available, we use the enthalpies which are known as the bond enthalpies. So please remember, bond enthalpies are the enthalpies which are required to break the bond. So see, break the bond, that means first we take reactants and then we minus the products or bond enthalpies of products from them. The net enthalpy change of a reaction is the amount of the net enthalpy change of the reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Please remember that the enthalpy of reaction is the energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the products. Remember, this is the formula we are going to use when we have the values given in the form of the bond enthalpy, but not in the form of the enthalpy of formation. Remember, this relationship is approximate and is valid when all the substances that are reactants and products are in the gaseous state. Now we want to study about the enthalpy of bond formation. Now see, this bond dissociation enthalpy and enthalpy of bond formation are different. So bond dissociation enthalpy is the enthalpy that is when the bond is being broken, and enthalpy of bond formation is the enthalpy that is related to the making of bonds. Enthalpy of bond formation is the enthalpy change when one mole of particular type of bond is formed from the gaseous atom. If we use enthalpy of bond formation, please remember that if we use the enthalpy of bond formation, then the enthalpy of reaction is equal to enthalpy of bond formation of products minus enthalpy of bond formation of the reactants. So this is where we use the normal or general formula, but that is what it is when we use the enthalpy of reactants and products, which is given into the enthalpy of bond formation, not in the enthalpy of bond dissociation, or it is not as the enthalpy of bond enthalpy. So this is how, my dear students, we understand about bond enthalpy and enthalpy of bond formation. Now we want to study about the enthalpy of solution. In whatever discussion we have done, if you want to ask something, you can ask, my dear students. बच्चों, अगर आप कुछ पूछना चाहते हैं तो आप पूछ सकते हैं. कुछ पूछना चाहेंगे क्या बच्चों? मुझे जवाब दीजिए. हेलो, क्या आप मुझे सुन पा रहे हैं?
Yes, sir.
Yes, sir.
कुछ पूछना है?
No, sir.
Okay.
No, sir.
Let's move on. Enthalpy of solution. Let us try to. So delta solution enthalpy bar. Definition, let's understand the definition. Enthalpy of solution of a substance is the enthalpy change when 1 mole of substance is dissolved in the specific amount of solvent. So please understand that enthalpy of solution of a substance is the enthalpy change when 1 mole of substance is dissolved in the specific amount of solvent. Please remember, the amount of solvent should be specific. Enthalpy of solution is infinite dilution. So this is the another definition. Enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interaction between the ions or solute molecules are negligible. So my dear students, when we do the dilution to the infinite level, the interaction between the various ions, or the interaction between the solid molecules is almost negligible, and that is what it is the condition. We call it as an infinite dilution. When an ionic compound dissolves in a solvent, the ions leave their ordered position from the crystals. These ions are now more free in the solution, but solvation of these ions, that is hydration in case of solvent, or in case of water, also occurs. So my dear students, when an ionic compound actually dissolves in water, the ions comes out from their ordered position, and then their hydration or solvation takes place. The solvation in case of solvent is water is known as the hydration. That is what we need to remember. So this is shown diagrammatically here. You can see that we are trying to understand it. Suppose we have an ionic compound AB. So first, when ionic compound AB turns out into the ions A plus and B plus, the energy is known as the lattice energy. Then, my dear students, these ions are being hydrated. So we need the, or so we, the energy change at that time we call it as a hydration energy, and thus the solution takes place. So A plus turns aqueous and B minus turns aqueous when two process takes place. One process energy related to it is known as lattice enthalpy. Second process of hydration takes place where the energy related to it is known as the hydration enthalpy. The enthalpy of solution of AB and overall, the sum of both these energy according to the Hash law of constant heat summation, we call it enthalpy of solution. So we can say that enthalpy of solution is the sum of the enthalpy, lattice enthalpy and hydration enthalpy. That is what we understand from this diagram. The enthalpy of solution of AB solid or enthalpy of solution of AB solid denoted by delta solution H bar in water, therefore determined by the selective values of the lattice enthalpy and enthalpy of hydration of the ions. So my dear students, we can write that solution enthalpy of solution is equal to enthalpy of lattice enthalpy and plus enthalpy of hydration. In most of the ionic compounds, enthalpy of solution is positive. That means the energy is required, and the dissociation process is endothermic in nature. So as the energy is required, we call it an endothermic process. Therefore, solubility of most of the salts in water increases with the rise in the temperature. So as you increase the temperature, most of the ionic compounds, they dissolve more into the water because the dissociation of ionic compound into ions is an endothermic reaction and energy is required for that particular process. If lattice enthalpy is very high, the dissolution of compound may not take place at all. So some compounds, some ionic compounds, they have very high enthalpy or they have very high lattice enthalpy, and that is why the dissolution does not take place easily. This is the reason why many fluorides tend to be less soluble corresponding to the chloride. So fluoride compounds, they generally have the very high lattice enthalpy, and some of the fluoride compounds like calcium fluoride, CaF2, they are they are not soluble in water because they have got very high uh, they have got very high lattice enthalpy. Now let us understand the definition of the lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in the gaseous state. Once again, the lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in the gaseous state, my dear students. You can see that this is NaCl solid, which turns out to be Na plus gas and Cl minus gas. The energy exchange is known as the lattice enthalpy, and lattice enthalpy for sodium chloride is plus 788 kilojoule per mole. That means the energy is required actually to break NaCl into ions Na plus and Cl minus. Since it is impossible to determine lattice enthalpy directly by experiment, we can use both the we can use the indirect method. We can use the indirect method where we construct an enthalpy diagram called Bohm-Haber cycle. So, my dear students, practically it is not possible to find out the or to measure the enthalpy, which is known as the lattice enthalpy, and that is why to understand the changes that are taking place during the formation of solution, we use or we draw a diagram which is known as the Bohm-Haber cycle. So, my dear students, here we are going to study about the new diagram which is known as the Bohm-Haber cycle. So this is what it is known as the Bohm-Haber cycle, my dear students, for you. You can look at this. In this page, I have shown you the Bohm-Haber cycle. Now this Bohm-Haber cycle, we are going to study it in detail. One by one processes we will understand, and then I'll explain it to you. Let's move and understand the Bohm-Haber cycle to find out the lattice enthalpy. Now, this is what it is based on the process of dissolution, my dear students. So, let us now calculate the lattice enthalpy of NaCl by following steps. So, we will have the following step. First thing that we study here about is the sublimation of sodium. So when sodium solid is sublimated to the sodium gas, we get sodium gas, my dear students. Now this is what we are trying to study, exactly opposite to it, that how this NaCl is formed. We are trying to study how NaCl is formed, and that is why we take sodium solid in the elemental form and we sublimate it to the sodium gas. The energy involved in this process, that is the energy of sublimation of sodium metal per mole, is 108.4 kilojoule per mole. Now, my dear students, what happens? The sodium gas which is obtained is converted into sodium ion and one electron. This is the process which is known as the ionization, and that is why the ionization enthalpy in this reaction is 496 kilojoule per mole. Next one is, my dear students, that our chlorine which is available 1 by 2 Cl2 gas turns into Cl gas. Actually, the reaction takes place as Cl2 gas that turns to the 2Cl gas, and the enthalpy change during this reaction is 242 kilojoule per mole. But my dear students, we want only one Cl for NaCl, so this value of this enthalpy change has to be divided by 2, and that is why here, my dear students, during this we can write that 242 by 2 kilojoule per mole energy is exchanged. The dissociation of chlorine, the reaction enthalpy is half the bond dissociation enthalpy of chlorine, and that is why, my dear students, we understand it that the dissociation enthalpy of chlorine-chlorine bond is, here we want to use it as a 121 kilojoule per mole. Here we want only one chlorine instead of two chlorine. We just need one chlorine to form NaCl, and that is why the enthalpy change associated with this is 121 kilojoule per mole. Here you can see that I have in front of me NaCl. So this NaCl, how it is formed? So we start it from here, my dear students. We start here, we start it from here, that first we take the sodium solid and chlorine gas. This sodium solid is first converted into sodium gas by the process of sublimation. During this process, energy is required, and that is why we have upside arrow. Then, my dear students, this sodium gas is converted into sodium plus gas, that is the ionization takes place, and again for ionization we need energy, and that is why the arrow is going up. Then, my dear students, it's term for chlorine. So chlorine 1 by 2 Cl2 gas uh, turns into Cl gas, and during this process 1 by 2 Cl2 gas turns into Cl gas. This is the bond dissociation enthalpy, which is 1 by 2 the bond dissociation enthalpy. That is what we have studied. So now we have sodium plus gas and Cl gas. This Cl gas, my dear student, in the next step, Cl gas get one electron, so which is known as the electron gain enthalpy. You can see here that Cl present here actually takes one electrons and turns out to be Cl minus, and this enthalpy related to this process is known as the electron gain enthalpy, because chlorine gains one electron. When chlorine gain one electron, the energy is released, and that is why the arrow is downside and the value of delta H is minus. Now what happens, my dear students? This Na plus and Cl minus, they combine with each other and energy is released. This energy is also known as the lattice enthalpy, and thus when Na plus and Cl minus combine, we get NaCl solid. Remember here, my dear students, that when Na plus and Cl minus give NaCl, it is also known as the lattice enthalpy. Delta H related to this is also known as the lattice enthalpy. And when it comes to NaCl, that gives us Na plus and Cl minus. This is also known as the lattice enthalpy. But the sign, if it is positive here, then here the sign is going to be negative. That is the major difference. So during the formation of NaCl, my dear students, all all the all the steps we have studied, and if we really study that when 1 mole of NaCl is formed, then the formation enthalpy is minus 402 kilojoule per mole. So during this process, when NaCl is formed, the formation enthalpy of NaCl is minus, that is the energy is actually released. Now we are not aware of this. We already have this value, that is the total amount of energy that takes place during these reactions. So here we can say that while forming the NaCl, the enthalpy of formation is the sum of the enthalpy of sublimation, and then ionization, and then 1/2 bond dissociation, and then electron gain enthalpy, and then lattice enthalpy. But we have these values of formation enthalpy, sublimation enthalpy, ionization enthalpy, bond dissociation enthalpy, and electron gain enthalpy. So here, using these values from this equation, we can find out the lattice enthalpy. So let us, this is how we are going to use the hash law of constant heat summation. Whatever the diagram we have drawn is known as the Born-Haber cycle, and using Born-Haber cycle, we can calculate the lattice enthalpy. Please understand, my dear students. So here we have seen that chlorine gain 1 electron and energy is released, and that is what it is known as the electron gain enthalpy. And the last step, this Na plus and Cl minus, they combine to give Na, NaCl, and here we, this enthalpy change, we call it as a lattice enthalpy. Now, according to the hash law of constant heat summation, we know that enthalpy of formation is the enthalpy of sublimation plus enthalpy of ionization plus 1 by 2 bond dissociation enthalpy plus enthalpy of electron gain and lattice enthalpy. And that is why lattice enthalpy is equal to delta formation of H, that is formation enthalpy minus sublimation enthalpy minus ionization enthalpy minus bond dissociation enthalpy and minus electron gain enthalpy. And that is how we get minus 788 kilojoule per mole, my dear students. So here the lattice enthalpy that we get is minus. It shows that when Na plus and Cl minus combine, when Na plus and Cl minus combine and they give NaCl, energy is actually released. But when we look at the definition of the lattice enthalpy, change in the internal energy, but when we look at the lattice enthalpy in the form of the enthalpy of solution, then my dear students, we need to understand that the reverse process takes place, and NaCl is converted into Na plus and Cl minus, and that is why for dissolution, when we write the lattice enthalpy, this sign we will change and this sign we will put as a positive. Now we want to calculate the internal energy change when lattice enthalpy is this. So for the reaction Na plus and Cl minus, we get NaCl. Here the Na plus and Cl minus combine with each other, and for this reaction the enthalpy change is minus 788 kilojoule per mole. But for the reaction NaCl give Na plus and Cl minus, the lattice enthalpy change involved in this reaction, we will have to change the sign, and we will write lattice enthalpy is equal to plus 788 kilojoule per mole. Now we know that change in internal energy for the reaction at 298 K, for this particular reaction when NaCl is converted to Na plus and Cl minus, the delta H is plus 788 kilojoule per mole. Now we know that delta H is equal to delta U plus delta N gas RT. Let us find out the delta N gas here. So for product side we have 2 moles, for reactant side we have 1 mole. Sorry, for reactant side we have 0 mole because there is no gaseous substance available, and delta N gas is equal to Np minus Nr, and here delta N gas is equal to 2, my dear students. Now we can put the value of delta N gas here. So delta N gas is 2. You know that this is delta U. This is the value for delta H. That is the lattice enthalpy. This is the value for R, and this is the value of T. Now why we put 1000 here? Because the value of enthalpy of reaction is in kilojoule per mole, whereas the value of R in joule. To convert it into kilojoule per mole, we divide it with the 1000. and that is how we 788 is equal to delta U plus 4.95, and therefore delta U is equal to 788 minus 4.95, which gives us approximately the value of 783 kilojoule per mole, and the total internal energy change during the formation or during the dissolution is less than the total enthalpy change, and that is 783 kilojoule per mole. So my dear students, when 1 mole of NaCl, the lattice enthalpy is plus 788 and hydration enthalpy is minus 784 kilojoule per mole, and therefore the enthalpy of solution is equal to lattice enthalpy plus hydration enthalpy, that is 788 kilojoule per mole minus 784 kilojoule per mole, and approximately the enthalpy of solution is plus 4 kilojoule per mole. It means when a substance or when NaCl dissolves into the water, actually the energy is required which is taken from the surrounding, and that is why dissolution of NaCl actually uh, uh, causes the cooling of the surrounding. So this is how, my dear students, we understand the dissolution of NaCl is accompanied by very little heat change. The process is endothermic in nature. Please remember that energy is required for the dissolution of NaCl rather than the energy is being released. So this is how, my dear students, we understand the Bohm-Haber cycle and the other various processes. Let us revise the discussion that we have done